Previously, we derived an expression for the electric potential from the special case where we had a test charge being pushed away from the source purely under the action of the internal Coulomb force of the system. Now we will look at a more general case where a test charge travels along some arbitrary path in the vicinity of a source, and we will show that we can derive exactly the same expression for the electric potential produced by the source. We start by looking at the motion of a test charge between some point A and another point B, and we will be concerned with finding out what the change in potential energy of the system is as the test charge moves from A to B along some arbitrary path. In order to do this, we will have to calculate again the amount of work that is being done by the internal force on the test charge, as we know that this is related to the change in potential energy of the system. In order to evaluate the amount of work that's being done on the test charge, we need to break up the path followed between A and B into a number of tiny displacements ds. If we zoom in on one of these tiny displacements, we see that we've got our displacement vector ds at some angle with the radial vector, which gives us the direction of the electric field produced by the source. We know that the amount of work done over this displacement is given by the expression shown on the screen, and if we choose our displacement to be small enough, to a good approximation, the electric field at the start and end points of this displacement will be the same. This means the amount of work done for this displacement reduces to the expression shown on the right. In general, for a point charge, we know that the electric field it produces is given by this expression, which gives us a new expression for the amount of work done on the test charge for the displacement ds. This expression is complicated because the dot product between r hat and ds changes for different points on the path. So let's look at the dot product more closely and see if we cannot reduce it to a more easily handled or shape that is more easily handled. If we look at the triangle formed by ds at its hypotenuse, we see that the dot product between the radial unit vector and ds just evaluates to the component of ds parallel or along the radial direction. This gives us a particularly simple expression for the amount of work done on the test charge for this tiny displacement, now purely in terms of the radial distance r. We can integrate this expression between the beginning and final position of the test charge to give us the work done on the test charge by the internal force as it moves from A to B. And from the work energy theorem, because this is the work done by an internal force, we know this has to be equals to the negative of the change in potential energy that the system experiences. This change in potential energy can be written in terms of the test charge and then a number of quantities that purely depend on the source and points in space around the source. From this, we can define the potential difference between 2 points, your point A and point B, as the expression shown by just dividing the change in potential energy by the test charge itself. This leads naturally to the definition of the electric potential at a point R away from the source. This is very similar to the expression we found previously for the special case, where the test charge moved only under the action of the internal force. Note that the potential therefore assigns a scalar value, which we call the electric potential, to every point around the source charge. The meaning of this scalar value is that it is the amount of potential energy that the system would have if a charge of 1 Coulomb were to suddenly pop into existence at that point R.